Same example. Let's now look at part B. A sample of 71 people gave mean breathing rate, again a complete cycle in and out, of 17.44 breaths per minute and standard deviation 7.99 breaths per minute. So obviously this sample is exactly the same sample as we have done in part A of our same example here. At significance level 0.001 is the sample showing strong evidence that mean breathing rate is higher than 10 breaths per minute. So based on the wording of the question here, is the sample showing strong evidence that mean breathing rate is higher than 10 BPM. So that means immediately as scratch work, mean breathing rates can be regarded as a population mean value. And then the problem asked us to find out if we have enough evidence to show that mean breathing rate should be higher than 10. Recognizing an inequality statement here. Now we can write down for ourselves the alternative hypothesis. So H sub 1 says mu is suggested to be greater than 10 by observing the sample. And so easily from identifying the alternative hypothesis, we can now identify our null hypothesis by simply replacing this inequality symbol with the equal sign. So our statement becomes mu equal 10. Our alternative hypothesis here has the statements with the inequality pointing to the right hand side or reading greater than. So the testing problem that we are doing will be a right tail test, or will be carried out as a right tail test. Back to the wording description on the screen here, then it looks like we're using the exact same sample as that in example 1. So very similar arguments there. 71 people will be the sample size. This is our sample mean. And this standard deviation here, similar to the argument I made in part A of this same example. This is our sample standard deviation. Or in other words, now as far as given information, we have an X bar given at 17.44. That's our sample mean value that we're using as a test to test this hypothesis. Our sample size is at 71, or n equals 71. Our sample standard deviation is notated by s. Lowercase s equals 7.99. And so now, again, since we're looking at a sample that came out from sample size 71 here, we must now again realize that our sample is only one sample among infinitely many others. And so we can generally represent all of those sample means at size 71 by a random variable capital X bar 71. So now my random variable capital X bar 71 represents the mean breathing rate in a sample, in any sample of 71 people, or in short of 71. And so just the same and the similar argument, since we now realize that this random variable capital X bar 71 represent an entire population of sample mean values, then there will be a population mean of all sample means existing out there. And central limit theorem stated that this mu X bar should equal value with mu. Therefore, in that way, consequently, now our null hypothesis started out stating that mu equals 10. So in the same logical argument I've made throughout example 1 and the earlier parts of this example 2, then I'm starting out by saying, if we accepted h sub 0, if we accepted the value claimed in our null hypothesis to be the truth, so if h sub 0 was true, then our null hypothesis started out stating that mu equals 10. So in the same logical argument I've made throughout example 1 and the earlier parts of this example 2, then I'm starting out by saying, if we accepted the value claimed in our null hypothesis to be the truth, so if h sub 0 was true, meaning we're accepting mu equal 10, then consequently, based on the central limit theorem, it leads to that mu x bar supposedly equals mu, but now will equal 10. Central limit theorem stated that sigma x bar, the average spread on this population, can be found by sigma over square root of the sample size, which is in our case consequently 71, since we are using 71 people in a sample. But now again, if we're looking back at this wording description of our example 2 part B, the entire wording description of this problem we're currently having is only about a description of the sample that we're currently having right here. Or in other words, my point I'm trying to address here is that we never knew, since part A, we never knew any information regarding the beginning population where we selected this sample from. We didn't know the population mean, we did not know the population standard deviation. And so as a consequence, the standard deviation written in our problem is only part of the description of this current sample that we're having. So this standard deviation is only a sample standard deviation value. It cannot be used as a sigma. And so as a further impact, this problem of ours, we are testing the hypothesis without knowing sigma. So we have unknown sigma or not given. Okay, our sigma value is unknown or not given. So as a further impact, without having a given sigma value, we won't be able to find the value for our sigma x bar. But keep in mind, it does exist out there. It's just that we are not able to find a value for it. It's all due to the fact that we have unknown sigma value here. Our sigma value is unknown. It's not given to us. On the other hand, our current sample size that we are using, being 71, is well above 30, making it true that this sampling distribution, or the population of all sample mean values at size 71, will be normally distributed at the center 10 with, unfortunately, the unknown sigma x bar value, which is acting as the average spread. So we have a known center, but we have an unknown average spread on this population of sample mean values. So think about, if we had our sigma for this problem, then the next step would be calculating the z-score for our sample. And the way of doing that, from where our sample mean is, we're going to subtract the center on the bell curve on the normal distribution, which is now accepted to be 10, and we'll divide by sigma x bar. But unfortunately, we have an unknown sigma x bar value. So as I said again, if we had sigma, then we would go ahead and proceed into, as the next step, calculating our sigma x bar value. But now, since we have an unknown sigma value and consequently an unknown sigma x bar value, our plan to calculate z-score for our sample fails. Or in other words, we won't be able to find the z-score for our sample. So based on similar argument we have made in part A of this example, since that route, finding sigma x bar, fails, then we can use an alternative. So now I am going to calculate, instead of z-score for our sample, I am going to calculate a t-score for our sample. And the t-score of our sample is going to be calculated as from where our sample mean value stands. I am going to subtract the center on the bell curve, just like that again. But now this difference is going to be divided by the expression 7.99 divided by square root of 71. And so now recall from the formula that I introduced as part of our part A in this current example here, then T star is given by the formula from wherever our sample mean is. We're subtracting the center, the accepted center on the bell curve, which is notated by mu sub 0, or the same as this value being claimed in the null hypothesis. And we're dividing that difference by S over square root of n. And that is the formula again for calculating T star. So calculation shows that our T star for this sample is positive 7.846. The actual calculation came out with a lot longer decimal, and unless being specified otherwise, usually for T star I'll calculate for 3 decimal places. But so now think about the T star here simply as a close enough replacement of the Z score to our sample that we were unable to calculate due to the missing value of sigma x bar. So if we actually had a known sigma value, which consequently led to having a successful sigma x bar, then our Z score would be somewhere actually close enough to this value. So here our T star is a reading about 7.846. So if we would be able to have a Z score, then Z score would be somewhere around in the 7s. Think about sigma x bar itself. It is sigma over square root of n. And so our T star formula utilizes that formula, S over square root of n. So this part in the denominator of our T star calculation is almost identically the same with the sigma x bar value, except for we replaced our sigma with our known sample standard deviation. And keep in mind that the advantage of using sample standard deviation is that we can always have a sample standard deviation. As long as we pick up a sample, we will always be able to calculate for ourselves a sample standard deviation. And so now having a T star score which is tentatively close enough to the Z score of our sample, then the next step now is to calculate the p value for our sample. So now we can imagine that if we would be on that bell curve, and we are on a bell curve. So imagine that our sample is on that bell curve where the center is at 10, and this bell curve has a common area being big fat in the middle here, and outside of the common area there is an unlikely area shaded in red here to the right hand side of our common area, and another exactly symmetric area shaded to the left in red as well, being an unlikely area to the left outside of my common area. So back to what I was in the middle of saying, our sample now is known to be somewhere to the right hand side of the center on this bell curve, but we would like to calculate, we are getting into calculating the p value of our sample to determine whether our sample will whether or not fall into this red unlikely area outside of the common area and to the right. And that is the reason why, again, same logical argument with how I have explained in earlier videos. And that is how I call this test here a right tail test. So p value now can can be calculated as the following setup. Among all sample mean values at size 71, we want to calculate the chance, the probability that we're going to find a sample mean at this sample size being greater than or equal 17.44. And so at this step right here, this p-value is graphically represented as an area tentatively shaded to the right from wherever our sample can be on this bell curve. If we had a known value for sigma in the beginning, then consequently we would have sigma x bar, then consequently we would have a z-score. Then this calculation would be calculated by running the LS&D program and subtract the answer from the LS&D program from 1. But now since we fail to have a z-score, so we won't be able to run LS&D program due to the fact that LS&D program will ask for a z-score, and we won't have a z-score value given for LS&D program. So now since we can't run the LS&D program, we come up with a workaround. We can, instead of using LS&D program, we are going to use the program that's called LTCDF program, where running it will ask for a t-score. Now I'm going to give positive 7.846, and this program will ask for, in addition, a degrees of freedom. Our degrees of freedom here in our sample is going to be from where the sample size we are subtracting 1. So our degrees of freedom required to run this LTCDF program is at 70. So that means at the bottom line, I am going to be running the LTCDF program with given t-score to be 7.846 and degrees of freedom at 70. But just again, imagine that the functionality of this LTCDF program is exactly the same as the functionality of the LS&D program. Then the answer coming out from here, from this program, is supposedly the area that would be shaded to the left from where our sample is on this bell curve. But that's not the answer we're looking for. That's not the area we're actually looking for as being shaded here in the picture. So that means we would need to subtract that answer coming out from LTCDF program from 1. Let's now have a look at the LTCDF program on my computer screen here. The program was made for students learning stats with me. For public viewers out there, there are other web resources that serve the exact same functionality. So in my particular LTCDF program right here, this box is asking for t-score. So our t-score is 7.846. And then I am going to head over to the degrees of freedom. So now I am going to enter 70. And our left area, our area shaded to the left of our sample, the area shaded to the left of our sample is supposedly, according to what you have seen on the screen there, supposedly something big enough or close enough to 1. But we now need to subtract this left area from 1 to obtain our designated area shaded to the right hand side of our sample. So the answer here comes out to be 0.0000. So I'm using a decimal. 0.0000 here is to indicate that our final value is a value so small, close enough to 0, so that even in 4 decimal places, it's still all 0 out. Back in the wording of the problem, our problem gave us a significance level to be at 0.001. So now comparing our final p-value being 0.000 with our given significance level given from in the problem, 0.001. The direct comparison shows that our final p-value of the sample is way below this significance level given in the problem. So the very same argument I have made in throughout example 1, then this is good for us to make a conclusion that our sample mean here is for sure among the unlikely values. And X bar being among the unlikely values leads to a stronger conclusion that our X bar itself is an unlikely value, indicating that it's not easy to get a sample like this if we accepted this claim right here. It is an unlikely value. The significance level is indicating that the chance of running into any value in this red area is only 0.001 chance, which is in decimal a 0.1%. But we have just now proven based on the p-value that our sample is right inside of that. And so if you want to see the detailed explanation, you can go ahead and view my videos for example 1 of testing a hypothesis about mu right there, and all that explanation is there. So now, having our X bar as an unlikely value, we can lead to another conclusion now, saying that our X bar is showing strong evidence. Our sample mean is showing strong evidence, or it is itself a strong evidence. Okay. And having strong evidence here for the purpose to reject the hypothesis, the null hypothesis, H sub 0. Or another way of saying, we have X bar as strong evidence to support our alternative hypothesis, H1. Now back to the actual wording of the question itself, of the problem itself. Then in the way how the question is worded, it is ultimately a yes or no question. Is the sample showing strong evidence? In our conclusion, just now we stated that our sample is showing strong evidence. So the ultimate answer to this question, to the question I have just now shown on the computer screen, is yes.